Okay, so that's the background on the KdV equation. Let's talk first a little bit about dispersion. If you remember way back, I think in the first couple weeks of the semester, we talked about dispersion, and in particular, how sort of the speed of different wave numbers is related. Now, if you have different wave solutions of your problem, you could think, well, the waves may not disperse from each other. All waves are going to sort of hang close together no matter what their shape is. But we already know through the example that I drew that waves that are kind of different shapes are going to move at different speeds. So you should expect then to have a non-trivial dispersion relation that will tell you how different sort of spatial widths of waves determine their speeds. We can't do this cleanly in the nonlinear equation, but we can do it in the context of a linearization of the KdV equation. Okay, so essentially the idea of dispersion is that you can have many waves and they're all going to have different speeds. Okay, so to study this, we'll just linearize our equation. And in particular, in order to get something non-trivial, let's linearize about u equals 1. Okay, so we have some sort of baseline level of our unknown variable, and let's say we perturb it. We perturb the shape of that. Okay, so in that case, if I take u to be equal to 1 plus epsilon v, okay, plus some higher order terms that are order epsilon squared, okay, then I can plug that in to my equation and just keep the linear and epsilon terms. So this will be a little bit of a perturbation calculation. So let's first of all remember what KdV equation is, right? KdV equation is u sub t plus ux plus gamma uxx, x equals 0, okay? And the idea of doing this, right, is we're going to plug things in, we're going to cancel out the stuff that's like order 1, and we're just going to leave the stuff that's of order epsilon. And you should think to yourself, if I see a linear term, this expansion should just pass through and I'll just keep the linear terms, right? The nonlinear terms are the only ones where you're going to have to do a little bit of work to see what comes out, right? So you have to expand that term out. So this is then, if I make this approximation and I drop the order epsilon squared terms, then I'm just going to get 1 plus epsilon v differentiated with respect to t, 1 plus epsilon v times 1 plus epsilon v differentiated with respect to x plus gamma 1 plus epsilon v differentiated thrice with respect to x, okay? So this term here is going to go away, right? So we just get epsilon vt plus 1 times the derivative of the 1 term here is just going to be 0. So I get a 1 times the epsilon the x term, and then I get the epsilon v term here is, if I just multiplied it by the derivative of 1, right, that would just be 0. And then I have plus an epsilon squared v vx term here, right? So because I only want to keep the terms of order epsilon, right, I would drop that from my expansion. And then I have plus gamma epsilon v xxx equals 0, okay? So because I only want the order epsilon terms, right, then I end up with, when dividing through by epsilon v sub t plus v sub x plus gamma vxxx equals 0. Okay. Now, the thing you do often in this case with nonlinear equations is you say, well, if I make a further assumption of what this function v is, then I can just learn something about the linear instability of the of different modes of perturbation to my to my linearized equation. And so one thing you can do in this case is assume that Vxt is of the form phi of t times e to the I kx, basically because we want to investigate different wave modes, okay? So when we have components in our solution of different spatial frequency, we want to know how those are going to evolve in time, because those are your different wave modes. So if you plug this into your PDE, then what you get is phi prime of t e to the I kx plus I k phi of t e to the I kx minus gamma I k cubed phi of t e to the I kx is equal to 0. Okay, so because it's a linear equation, that works as long as this equation is satisfied. So if we divide through by e to the I kx, we get phi prime plus I k minus gamma I gamma k cubed multiplied by phi is equal to 0. And we can solve this for phi of t is equal to e to the minus I k minus gamma k cubed t, where we'll just drop the multiplicative constant here. Okay, so depending on the particular mode that I have, okay, which is the particular wave solution, the shape of the wave, the spatial frequency of the wave, this equation tells me sort of how that is going to propagate in time. Okay, so this means that v is of the form e to the lambda t e to the I kx, which gives us a dispersion relation where lambda of k is equal to minus I k minus gamma k cubed. And so we call this the dispersion relation, okay? And it's going to be our time-dependent response of the wave with wave number k, okay? Or you could also think of that as sort of a spatial frequency, right? You can make sines and cosines out of complex exponentials. And so, yeah, that tells you something about disturbances in U with a certain spatial frequency, how they're going to propagate in time, okay? So there's two things to note about this, right? We can kind of decompose stuff in order to see how these different parts make up a traveling wave solution, okay? And how another term essentially alters the speed over time, okay? So if we write this out, right, if I have v of xt now is equal to e to the minus I k minus gamma k cubed, okay, plus I kx, I can actually group some things together, right? So if I write e to the, sorry, there should be a t here. If I group together I k, then I have one part of this that's just x minus t, okay? And this should be a little bit reminiscent of something from way back at the beginning of the semester, which is just the transport equation. So there's one piece of this solution that kind of just behaves like the transport equation, right? If that was the only thing that was in there, all that would happen is that everything would always get transported at the same speed, right? But this is a non-trivial equation, so we get an additional term that tells us essentially how waves of different shapes have their speeds modified. And so the other piece of the equation, right, is minus I, so I guess it'd be plus I gamma k cubed, right, times t. Right? Or in other words, this is equal to e to the I k, and now I'm going to put everything together, right? I have one part of this that's just t, but if I factor out an I k from this, then I get 1 minus gamma k squared times t. Okay, I think I've done that all right? So this is my k dependent wave speed. Essentially, it tells me that my waves are dispersive in this case. So waves that have a higher value of k will travel more slowly, okay? Because as k gets larger, this is going to shrink. I mean, of course, until this sort of switches sign, right? But let's assume that gamma is small enough that for all the k's of interest, we always keep this value positive. As you increase k, you're going to slow down the wave, okay? For lower values of k, right, this quantity is going to be smaller and your speed is going to be faster. So that means fatter waves should travel more quickly, okay? So you see here in this linear analysis. So remember, we're not even analyzing the whole nonlinear equation here. We're just doing a linearization analysis. Essentially, what we can show is that different shaped waves have different speeds in this equation. Okay, that's the first part of KdV equation. Let me take a breath. Are there any questions?
This kind of reminds me of von Neumann stability analysis for numerical PDEs.
Yeah, right. So where you sort of plug in an ansatz, you have a sort of a separated variable ansatz, and then you see how different terms in the approximation grow.
Yeah, I think so. It's been a while since I've done it, but the substitution of the eigenmodes kind
Yeah.
of.
Yeah, this is used all over in numerical and analytical PDEs. For sure, this is a common technique. It's not just used here. So, yeah, I don't know if there's some super set term for all doing this, but it's just a separated sort of space and time Stability analysis, yeah. And you can think of this as a stability analysis for sure. Okay. All right. Let's move on.